I am Professor Anish Vora and I welcome you all in this video lecture. In this video lecture, we will study about starting winding of single phase induction motor and how circle diagram can be useful in selection of appropriate values of the starting winding. In case of single phase induction motor, we know that without a starting winding or without auxiliary winding, only with a main winding, single phase induction motor has a zero resultant starting torque, and that is the reason why single phase induction motor is not a self-start motor. To make a self-start motor, we require to add additional auxiliary or starting winding. Now, in selection or in designing of starting winding, circle diagram will be very much helpful in visualizing starting winding. So, we start with a circle diagram. We have x-axis and y-axis. Y-axis we take as a voltage axis. Then we have starting current of the main winding, and that is making an angle with voltage axis, and that angle is known as theta m. M we use for main winding. It is making a very high angle with voltage axis, or in other words we can say that it is lagging behind the voltage axis with a very high angle because the reactance of the main winding is high and the resistance is less. Now suppose we have designed our main winding and now we are planning to design our starting winding. Suppose we now arbitrarily select number of turns of the auxiliary winding. When we select number of turns, we can have two parameters. One parameter, that is the ratio K, that is turn ratio. In previous lecture we have seen that how starting torque can be derived, the equation for the starting torque. So if we select number of turns, then ratio K can be derived, and XLA, that is a reactance of the starting winding, that can be also derived. So based on this, now only the variable parameter, that is the resistance of the starting winding, and resistance of the starting winding will decide total stator resistance. So based on selection of our starting winding parameters, we have starting current, we call it auxiliary winding, and it is making an angle with voltage axis, and that angle is known as theta A. A we use for auxiliary winding, and we can see that the angle starting current of the auxiliary winding is making with voltage axis, that is very less, and the reason is it has a very high resistance in the winding and the low reactance. So angle is very less compared to the angle which is making starting current of the main winding with the voltage axis, and that angle was theta m. So if we have both the current, then we can take diameter of the circle diagram, and that is V divided by XLA, where XLA, that is leakage reactance of the auxiliary winding. So that decides the diameter of the circle diagram, and we can draw the circle diagram. AC, that is actual starting current of the auxiliary winding, and locus of AC on the diameter AB, that is making a semicircle for the auxiliary current. So we have total starting current, and that is known as IS, and that is phasor sum of the OA and AC. OA, here we can see that OA, that is our starting current of the main winding, and AC, that is starting current of the auxiliary winding, and total starting current, that is IS, and that is phasor sum of the starting current of the main winding and starting current of the auxiliary winding. Now from the circle diagram, it is very clear that starting torque is proportional to ISA, that is starting current of the auxiliary winding, because ISM, that is starting current of the main winding, it is constant because we have set the parameters of the starting winding and we have fixed that parameter. So starting current for the main winding is constant. If we change the resistance starting winding, then accordingly starting current change. So starting torque is proportional to ISA, that is starting current of the auxiliary winding, and sine of theta m minus theta a. Again, if we go back to our circle diagram, now one thing is very clear, that starting torque is proportional to ISA and sine of theta m minus theta a. Now if we draw the torque line, and if we draw a perpendicular from torque line and joining to point C, then we can see that AC, that is a starting current of the auxiliary winding ISA, is making an angle with the torque line, that is theta m minus theta a. And from the geometry of the circle diagram, we can see that CK, that is a perpendicular line to the torque line, CK is exactly equal to the ISA sine theta m minus theta a. So we can write that starting torque is equal to CK, and CK, that is exactly equal to the ISA sine theta m minus theta a. If I go back to our circle diagram again, now you can observe and you can identify that CK, that is ISA sine theta m minus theta a. So that is what we have written, and it is our starting torque. So CK, that is ISA sine theta m minus theta a. So CK will give us starting torque. So from the circle diagram, it is very easy that the values we have chosen for the starting winding, and accordingly how much starting torque we are getting. So this circle diagram is very useful while designing our starting winding, and now we can change our values, resistance of the starting winding as per our requirement. Now maximum starting torque. For maximum starting torque, we have a condition that CK should be maximum in length. Now CK, we know that CK is our starting torque for the values we have selected for the starting winding. Values, number of turns will give us total leakage reactance and starting resistance. Now only the variable is starting resistance, and by varying starting resistance of the starting winding, we have overall variable starting resistance of the stator winding. So maximum starting torque, again we go back to our circle diagram, and maximum starting torque can be defined based on a point D. D is halfway on the arc between A and E. So we have AD must be equal to DE. That is halfway. And that point DK dash, the line gives us maximum torque. So as we discussed earlier that maximum starting torque CK should be maximum in length. So we have drawn D halfway between point A and E on arc. So AD is equal to D. Again, if I go back to our circle diagram, now you can see that AD and DE should be equal. Then DK dash, that gives us maximum starting torque. Similar way, AK dash should be equal to EK dash. So AK dash should be equal to EK dash. So DK dash give us maximum starting torque. So this circle diagram will be very much useful for defining appropriate values of starting winding. So thank you very much for watching my video. Keep watching. Thank you very much.